Yeah, so hello everyone, welcome to the European Non-Associative Algebra Seminar. I'm glad to introduce the talk of today by Brais Ramos Pérez from Universidad Santiago de Compostela. He's going to talk on twisted relative Rota-Baxter operators and their relation with Hopf's trusses. Please.
Okay, thank you very much for the introduction. And before starting, I would like to give thanks to the organizing committee for inviting me to give this talk in this seminar today. And okay, as the title says, the aim of my talk is to give a categorical relationship between the category of trusses and a new category that we are going to introduce in this talk, which is the category of twisted relative Rota-Baxter operators. So this work is motivated by a previous result by Li Shen and Tang, published in the Journal of Non-Commutative Geometry in a paper in 2024, where what they do basically is to construct a pair of functors, one from Hopf braces to the category of relative Rota-Baxter operators, which is a category that they introduce in this paper, and another functor on the other way around, in such a way that these two functors constitute an adjoint pair. So what we do in this work is that, motivated by the fact that Hopf trusses generalize Hopf braces, what we want to do is to construct here a new category, which will be the category of twisted relative Rota-Baxter operators, which are some structures that generalize these ones, together with a pair of functors in this setting that also constitute an adjoint pair. So what we want is to generalize this result by Li Shen and Tang. Okay, so if anyone is interested and if anyone want to consult the proofs of the results, all of them can be consulted in this paper published in Sigma very recently in 2025. Okay, so for this talk, we are going to be working in a braided monoidal setting. So we are going to denote by C to a strict braided monoidal category, a general braided monoidal category, which is a category endowed with a tensor functor, an unit object denoted by K, and a family of natural isomorphisms denoted by this little c, which is called the braiding. And we will also use the following notation. If P is an object of the category and F is a morphism, P tensor F will denote the tensor product of the identity of P with F, and analogously, F tensor P will denote the tensor product of F with the identity of P. So we will say that our category C is symmetric when the braiding satisfies this additional condition. Cxy with Cyx is equal to the identity of X tensor Y. In other words, this equality means that the inverse of the braiding is the braiding itself. So these kind of categories constitute a broad class, and some examples can be the category of sets, the category of modules over a commutative ring R, and then the category of vector spaces over a field, the category of representations of a group or the braid category. These are some of examples. So in this talk, I assume that all the people is somehow familiar with these notions, the notions of algebra, coalgebra, bialgebra, Hopf algebra, and modules over a Hopf algebra in a braided monoidal setting. But for this talk, the non-unital version of these structures will play an important role. So first of all, we are going to start by defining this non-unital version of these structures, of some of these structures. So first of all, we are going to introduce the notion of non-unital algebra. So a non-unital algebra is a pair A mu A, where A is an object of the category and mu A is an associative product defined on A. That is a morphism mu A from A tensor A to A, satisfying the usual associativity, which is this equality here. So a non-unital algebra is said to be an algebra when there exists a unit morphism eta A from the unit object of the category to A, satisfying this equality here, which is the so-called unit property, and that means that the unit with the product in both sides is equal always to the identity of the object A. So the notion of non-unital algebra gives rise to the notion of non-unital bialgebra. So a non-unital bialgebra is an object B of our category such that with an associative product mu B, this pair is a non-unital algebra, and with a counit and a coproduct, it has to be a coalgebra, satisfying that the associative product mu B has to be a coalgebra morphism. So again, a non-unital bialgebra is said to be a bialgebra when there exists a unit morphism eta B from K to B, such that this triple is now an algebra and satisfying that the unit has to be a coalgebra morphism too as the product. Both of them have to be a coalgebra morphism. Okay, so another definition that is important is the notion of non-unital module over a non-unital bialgebra. So we are going to take B a non-unital bialgebra, and we will say that a non-unital left B module is a pair M phi M, where M is an object of the category, and phi M is a morphism from B tensor M to M, which is called the action of the module, satisfying this equality here. B tensor the action with the action is equal to the product mu B tensor M with the action. So a non-unital left B module is said to be a left B module when B is a bialgebra with unit eta B, such that now the action satisfies this additional condition. The unit tensor M with the action has to be equal to the identity of M. So in this case, we will say that the pair M phi M is a left B module. So if we have M and N non-unital left B modules, a morphism F from M to M is said to be a morphism of non-unital left B modules if this additional equality holds, which means that the morphism F is bilinear. Phi M with F is equal to B tensor F with the action phi M. So an important situation is the case appears in the case that this object M is, for example, an algebra. What happens is if N is an algebra and how the unit and the product of the algebra are compatible with the action of the module. So this situation is what gives rise to the notion of non-unital left B module algebra. So in this case, we have A an algebra, and we will say that a pair A phi A is a non-unital left B module algebra when, first of all, A with the action phi A is a non-unital left B module, satisfying that the unit and the product of the algebra are both morphisms of non-unital left B modules. In other words, these two morphisms, the unit and the product, are bilinear, and this is exactly the same as the fact that these two equalities hold. In the same way, if D is now a coalgebra, a pair D phi D is going to be a non-unital left B module coalgebra when D with phi is, first of all, a non-unital left B module, and also the counit and the coproduct are both bilinear morphisms, which means that these two equalities here hold. And it's easy to see if we have a look at these two equalities that the fact that these two equalities here hold, that is, D phi D is a non-unital left B module coalgebra, if and only if this action, phi D, is a coalgebra morphism and with D constitute a non-unital left B module. So this is an equivalence. Okay, and an important example is the following. Always that we have H, any Hopf algebra in our braided monoidal category C, then H with the so-called adjoint action of H, which is defined in this particular way, is an example of left H module algebra. And if we assume also that this Hopf algebra H is co-commutative, then H with the adjoint action is going to be a left H module coalgebra too, because in the co-commutative setting, this action phi H adjoint is going to be a coalgebra morphism. Okay, so with these preliminaries in our mind, we can move on to the first section of the talk entitled Hopf braces and Hopf trusses, in which we are going to define these two structures. But first of all, to introduce the notion of Hopf brace, we are going to see first a brief introduction in order to see how these structures appear. So to speak about Hopf braces, we have to speak first about skew braces, which are some structures that were introduced by Guarneri and Bendramin in this paper published in 2017, where skew braces were defined as follows. A skew brace is a pair of groups over the same underlying set G, and satisfying this compatibility condition between the product denoted by a dot with the product denoted by a star. So in this paper, skew braces are presented as the suitable structures to give rise to non-degenerate and non-necessarily involutive solutions of the set-theoretical Yang-Baxter equation. So after that, but also in the same year, Angiano, together with Galindo and Bendramin, introduced the notion of Hopf brace. And in this paper, they are presented as the quantum version of skew braces. What does it mean? It means that Hopf braces appeared from skew braces by a process of linearization. So to be more precise, what is a Hopf brace in our braided monoidal category C? So we are going to consider that H with a counit and a coproduct is a coalgebra in our braided monoidal category C, and we are going to assume that H admits two different algebra structures. The first one with unit eta 1 and product mu 1, and the second one with unit eta 2 and product mu 2, two different algebra structures over H. So a Hopf brace is going to be a tuple like this, satisfying the following conditions. First of all, H with the first algebra structure and the coalgebra structure that we fixed before, together with an antipode, lambda H1 is a Hopf algebra, and this first Hopf algebra structure is going to be denoted by H1. In the same way, H, but now with the second algebra structure, the same coalgebra and another antipode denoted by lambda 2 is again a Hopf algebra, and this first Hopf algebra is denoted by H2. And as we can see, we have two different products, and then this compatibility condition between these two products holds, where here in this equality, as you can see here, appears a morphism that is denoted by capital gamma H1, and it is defined in this particular way. Graphically, the definition of this morphism capital gamma H1 can be represented in this way. Delta H tensor the identity, composed with lambda 1 tensor mu 2 with lambda 1. Okay, so from now on, to be the notation easier, I am going to denote Hopf braces in this way, H equal to H1, H2, emphasizing that in a Hopf brace, what we have is two different Hopf algebra structures defined on H, H1 and H2, with the particularity that both Hopf algebras share the same underlying coalgebra. As both Hopf algebras share the same underlying coalgebra, the following definition has sense. We will say that a Hopf brace is cocommutative when the underlying coalgebra is cocommutative. That is, when the coproduct with the braiding is equal to the coproduct. Okay, and these structures, Hopf braces, constitute a category whose morphisms are defined as follows. If we have two Hopf braces, H and B, a morphism F between the underlying objects between H and B is said to be a morphism of Hopf braces if F between H1 and B1 and F between H2 and B2 are both morphisms of Hopf algebras. And this category is going to be denoted in this way, HBR. Okay, so some examples of these structures. First of all, skew braces are examples of Hopf braces because the notion of skew brace is no more that Hopf braces, but considering that the underlying category is the category of sets. Another interesting example are Hopf algebras, because if we have any Hopf algebra H in our category C, then H always induces an example of trivial Hopf brace by considering that both H1 and H2, the two Hopf algebra structure, are equal to the Hopf algebra H that we are taking. So what we have in this sense is that T from Hopf algebras to the category of Hopf braces is a functor acting on objects in this way by sending a Hopf algebra H to the trivial Hopf brace, which is H1 equal H and H2 equal H, and on morphisms defined by the identity. And another example, maybe a little bit more interesting because it's non-trivial, is the following. If we assume that the base category C is symmetric, and we take in C two different Hopf algebras, H and X, cocommutative Hopf algebras, satisfying that H with an action, phi H, is a left X module algebra coalgebra, then over the tensor product of H with X, we can construct two different algebra structures. The first one is the usual tensor product of algebra, which is a Hopf algebra with antipode, the tensor product of the antipodes. And another example is the so-called smash product Hopf algebra, which is a Hopf algebra with the product defined in this way. So this second Hopf algebra structure, the smash product, is denoted in this way. So what we can prove is that the tensor product and the smash product satisfy the compatibility condition of Hopf braces, and then this pair of Hopf algebras is a new example of Hopf brace. Some properties that these structures satisfy are the following. If we have H and a Hopf brace, the first property that we can prove is that the unit for the first algebra structure, H1, has to be equal to the unit eta2 for the second algebra structure. Eta1 is equal to eta2, and this is a direct consequence of the compatibility condition between the products. Moreover, it's possible to prove that H1 with the capital gamma H1, that is the morphism that I defined before, gives rise to a structure of left H2 module algebra. Moreover, if we assume that the Hopf brace is co-commutative, then this action, capital gamma H1, is going to be a coalgebra morphism. And then this, in the co-commutative setting, this structure of module is also a structure of left H2 module coalgebra. And to conclude, it's possible to prove that the second product always admits this expression in terms of the first product and the action, capital gamma H1. Delta tensor the identity with the identity tensor gamma with mu1 is also always equal to mu2. Okay, and another important property of Hopf braces is that in this paper, Anjono, Galindo, and Bendramin not only present these structures as important from an algebraic point of view, but also from a physical, because they prove that any co-commutative Hopf brace H induces a solution to the quantum version of the Rota-Baxter equation. Okay, so once we have introduced the notion of Hopf brace, we are going to introduce now the notion of Hopf truss that appeared first in 2019 in this paper by Brzezinski, whose structure is very similar to that of the paper of Anjono, Galindo, and Bendramin. What Brzezinski does is first introduce the notion of skew truss, and then by a process of linearization, he introduces the notion of Hopf truss. The notion of Hopf truss arises. Okay, so this notion of Hopf truss is very similar to that of Hopf braces. So the definition of this object is the following. It's a Hopf truss is a tuple like this, satisfying the following. H1, as for Hopf braces, is going to be a Hopf algebra. But now H2 is not going to be a Hopf algebra. It is going to be a non-unital bialgebra. And also, since we have two different products, mu1 and mu2, these two products has to be compatible in the sense that this equality here holds. But now, in this equality, does not appear the morphism capital gamma H1. It appears a new morphism denoted by capital gamma H1 sigma H, which is defined in this particular way. Delta tensor the identity with sigma with lambda tensor mu2 with mu1, where this sigma H is what we call the cocycle, and it is no more than a coalgebra morphism from H to H. So in some sense, this morphism capital gamma H1 sigma H is no more than a modification of this morphism capital gamma H1 that we define in the Hopf brace setting by using a cocycle. So it's easy to see that when this cocycle sigma is the identity, then capital gamma H1 is recovered. And if we also assume that the structure H2 is a Hopf algebra, in the case that sigma is the identity, then any Hopf truss is a Hopf brace. And that's why we say that Hopf trusses are generalizations of the notion of Hopf brace. Okay, so the notation that we will use for these objects is very similar as for Hopf braces, but now we will use triples instead of a pair, where in the third component we are going to specify what is the cocycle, sigma H. And again, it's important to note that the Hopf algebra H1 and the non-unital bialgebra H2 both share the same underlying coalgebra too. So it's possible to define co-commutative Hopf trusses in exactly the same way as for co-commutative Hopf braces. H is going to be a cocommutative Hopf truss when the underlying coalgebra is cocommutative. That is when the coproduct with the braiding is equal to the coproduct. And again, these structures constitute a category if we define the morphisms as follows. F from a Hopf truss H to a Hopf truss B is going to be a morphism of Hopf trusses if between H1 and B1 this F is a Hopf algebra morphism, but this F between H2 and B2 is going to be a morphism of non-unital bialgebras. And we are going to denote this category in this way by HTR. Okay, examples. Again, we are going to, the example that we are going to give is skew trusses, because as happened for skew braces, skew trusses are Hopf trusses, but considering that the underlying category is the category of sets. And properties. Again, the properties are very similar to that of Hopf trusses, of Hopf braces, sorry, because we know that in the Hopf brace setting, the properties that we saw before is that H1 with the capital gamma H1 is a left H2 modular algebra. So the same happened for Hopf trusses. H1, but now with the capital gamma H1 sigma H, in this setting, it is going to be a non-unital left H2 modular algebra. Moreover, in the Hopf brace setting, we know that the action is cocommutative when the Hopf brace is cocommutative. The same happens for Hopf trusses. When the Hopf truss is cocommutative, the non-unital action capital gamma H1 sigma H, it is going to be a coalgebra morphism. And also, we know that in the Hopf brace setting, mu2 can be expressed in this way in terms of mu1 and the action gamma. The same happened here for Hopf trusses. The second product, mu2, admit this expression in terms of the first product and the non-unital action, but now here it also appears the cocycle in the Hopf brace, in the Hopf truss setting. Delta tensor the identity with the cocycle sigma tensor gamma H1 sigma H with mu1 is equal to mu2. And as a consequence of this equality here, it is also possible to prove that the cocycle sigma H is equal to H tensor the unit with the second product. And if we have F any morphism of Hopf trusses from H to B, then automatically holds that F commutes with the cocycles. Sigma H with F is equal to F with sigma B. Okay, so once we have introduced the notion of Hopf braces and Hopf trusses, and we have recalled some of their properties, we are going to move on to the second section, in which we are going to recall what is the categorical relationship between Hopf trusses and relative Rota-Baxter operators. So relative Rota-Baxter operators appear, as I said before, in this paper by Lixian and Tang, published in the Journal of Non-Commutative Geometry. And in this paper, these structures are presented as generalizations of Rota-Baxter operators on cocommutative Hopf algebras introduced by Goncharov in this paper published in 2021 in Journal of Algebra. Okay, so in Goncharov's sense, a Rota-Baxter operator over a cocommutative Hopf algebra H is a coalgebra morphism denoted by T from H to H, satisfying this equality 1. Mu bar with T is equal to T tensor T with mu H, where this mu bar here is a product defined in this particular way. So you can see that in the definition of this product, it appears here the adjoint action of the Hopf algebra H. So graphically, this condition 1 can be represented like this, T tensor T with mu H equal to mu bar, which is now this morphism here in blue, with T. Okay, so what is the idea followed by Lixian and Tang to introduce relative Rota-Baxter operators from Goncharov's Rota-Baxter operators? So what they do is to consider two Hopf algebras instead of only one Hopf algebra, H and B, such that H with an action phi H is a left B-module algebra coalgebra, and now the operator T is going to be a morphism from H to B, a coalgebra morphism, instead of an endomorphism of H, as happened before. So the condition that they impose is the following. Here on the left, we have the condition of T for being a Goncharov Rota-Baxter operator, and what they do is to change the adjoint action that appears here by the general action phi H of B over H. In the rest, it is exactly the same condition. Okay, so to be more precise, if we have H and B, two Hopf algebras, such that H with an action is a left B-module algebra coalgebra, then T from H to B is a relative Rota-Baxter operator if, first of all, T is a coalgebra morphism, and also this equality 2 holds T tensor T with mu B is equal to mu bar with T, where mu bar, this product, is defined as before, but changing the adjoint action by this action phi H. Graphically, it can be represented in this way, this condition number 2. Okay, so from now on, I'm going to denote relative Rota-Baxter operators in this way by using pairs, where the first component is the coalgebra morphism T from H to B, and the second component is the action phi H of P over H. And these objects constitute a category if we define the morphisms as follows. A morphism of relative Rota-Baxter operators from T to L is going to be given by a pair, Fg, where F is a morphism of Hopf algebras from H to A, G is a morphism of Hopf algebras from B to D, and also these two equalities hold. F with L has to be equal to T with G, and this compatibility condition with the actions holds. We are going to denote this category by a little r, rb. Okay, so what Lichen and Tang do is the following. First of all, they consider these two subcategories, COCHBR, which is the full subcategory of Hopf braces constituted by co-commutative Hopf braces, and RRB star, which is the full subcategory of relative Rota-Baxter operators whose objects satisfy that this Hopf algebra H here, that is the source of the Rota-Baxter operator T, has to be a co-commutative Hopf algebra. So what they do is, first of all, to construct a functor F from co-commutative Hopf braces to relative Rota-Baxter operators star, define it as follows. If we have a co-commutative Hopf brace H equal to H1, H2, F of H is going to be a relative Rota-Baxter operator given by the identity of H between H1 and H2, together with the action capital gamma H1, and define it on morphisms by the duplication. F of F is equal to FF. And on the other way around, they construct a functor denoted by G from relative Rota-Baxter operators star to co-commutative Hopf braces defined as follows. G acting over T phi H, a relative Rota-Baxter operator in this subcategory, is equal to the co-commutative Hopf brace denoted by H bar, where the Hopf algebra H1 is this Hopf algebra H, the source of the morphism T, and the Hopf algebra H2 is denoted by H bar, and it is a Hopf algebra over H, whose product is the previous product mu bar that I defined before, and the antipode, denoted by lambda bar, is defined in this particular way. On morphisms, this functor G is the projection into the first component. G of Fg is equal to F. Okay, so the main result by Lichen and Tang in this setting is that F and G constitute an adjoint pair, that is, F is left adjoint to G. So what we want to do for the rest of the talk is to try to generalize these results by Lichen and Tang for Hopf trusses. And to do so, the first we have to do is to construct the category of twisted relative Rota-Baxter operators. So to define what a twisted relative Rota-Baxter is, the idea that we have followed is the same idea that Brzezinski used to introduce Hopf trusses from Hopf braces. The idea is the following. Here on the left, we have the condition for T to be a relative Rota-Baxter operator, and what we have done is to modify this equality by using a cocycle in this way. We are going to introduce here in the condition a cocycle, psi h, which is again no more than a coalgebra morphism from H to H, but in this setting we are going to denote this morphism by psi h. It's easy to see that when this cocycle is the identity, then we recover this equality here, the previous equality for relative Rota-Baxter operators. Okay, so to be precise, if we have H a Hopf algebra and B a non-unital bialgebra in our category C, such that these two structures are related by a left bimodule algebra coalgebra structure, H with an action is a non-unital left bimodule algebra coalgebra, then in this setting, we are going to say that a coalgebra morphism T from H to B is a weak twisted relative Rota-Baxter operators if, first of all, T tensor T with mu B is equal to mu tilde with T, where now mu tilde is defined in this way. Here in the definition of this product is going to appear the cocycle psi h, which again, remember that is a coalgebra morphism from h to h. This product, when this cocycle is the identity, we recover the previous product mu bar. In the definition of weak-twisted relative Rota-Baxter operators, we have to add this second technical condition, which establish a compatibility condition between this product, mu tilde, with the cocycle. Mu tilde with the cocycle has to be equal to H tensor psi with mu tilde, which is somehow a condition of linearity. Okay, so from now on, we are going to denote these structures again using triples, where in the third component, we are going to specify the cocycle. And again, these structures constitute a category denoted WTRRB, whose morphisms are defined as follows. A morphism of weak-twisted relative Rota-Baxter operators from T to L is again a pair, FG, where F is a Hopf algebra morphism from H to A, G is a morphism of non-unital bialgebras from B to D. Also, these two equalities hold, which are exactly the same equalities as for relative Rota-Baxter operators, but we need to impose an additional condition, which is this equality here. That means that the Hopf algebra morphism F has to commute with the cocycles. F with psi of A is equal to psi of H with F. Okay, so when a weak twisted relative Rota-Baxter operator is said to be only twisted, so this subcategory satisfies this additional condition. A weak twisted relative Rota-Baxter is said to be twisted when the cocycle psi h preserves the unit. That is, when this equality here holds. Eta h with psi h is equal to eta h. And we are going to denote this subcategory in this way. Okay, so always that we are working with objects in this subcategory, if we assume that this the target of T, that is this non-unital bialgebra B, is a bialgebra with unit eta B, then if we work with twisted relative Rota-Baxter operators, automatically this equality holds. That is, T automatically preserves the unit 2 as the cocycle. Eta H with T is equal to eta B when we work in this setting. Okay, so what we have done in this paper in Sigma is the following. Again, we consider the following two subcategories, COCHTR, which is the category of concommutative Hopf trusses, and WTRRB star, which is the full subcategory of weak twisted relative Rota-Baxter operators, whose objects satisfy that the source of the Rota-Baxter operator T, that is this Hopf algebra H here, is commutative. So we have constructed the following two functors. First of all, the functor lambda from cocommutative Hopf trusses to weak twisted relative Rota-Baxter operators star, defined as follows. If we have a cocommutative Hopf truss H, H1, H2, sigma H, then lambda of H is equal to this triple identity of H between H1 and H2. Then the action is going to be the non-unital action capital gamma H1 sigma H. And then the cocycle is going to be the cocycle psi H itself, the same cocycle as the Hopf truss H that we are taking. And on morphisms, again, is given by duplication. Lambda of F is equal to FF. On the other way around, we have this functor omega from weak twisted relative Rota-Baxter operators star to cocommutative Hopf trusses defined as follows. If we have T phi H psi H, a weak twisted relative Rota-Baxter operator, omega of this triple is going to be a cocommutative Hopf truss that we are going to denote in this way by H tilde, where the Hopf algebra H1 is this Hopf algebra H, the non-unital bialgebra H2 is given by this non-unital bialgebra over H denoted by H tilde, which is a non-unital bialgebra whose product is the product mu tilde that I defined before. And the cocycle is the cocycle psi H itself. The cocycle of the Hopf truss is the same cocycle as for the weak twisted relative Rota-Baxter operator. On morphisms, this omega is again the projection into the first component. Okay, so first main result that we prove is that, as happened in the Hopf-Brais setting, these two functors here for Hopf trusses satisfy the same result. Lambda is left adjoint to omega, that is lambda and omega constitute an adjoint pair, as we want to. So, but in this setting, for Hopf trusses, we have gone a step forward, because if we consider this subcategory here, denoted in this way, WT RRB star ISO, which is the full subcategory of the previous subcategory of WT RRB star, whose objects satisfy that the operator T, the morphism T, is an isomorphism in the base category in C, then what we notice is that if we have any cocommutative Hopf truss H1, H2, sigma, then lambda acting on H is an object that always lives in this subcategory, in the subcategory WTRRB star ISO, because the identity is always an isomorphism in the base category. So to be more precise, this functor lambda is going to be a morphism from cocommutative Hopf trusses to this subcategory here. So the second main result of this talk is the following. Functors lambda and the restriction of omega to this subcategory induce a categorical equivalence between weak-twisted relative Rota-Baxter operators star ISO, this subcategory, and the subcategory of cocommutative Hopf trusses. So these objects, the objects on this subcategory, give an alternative description for cocommutative Hopf trusses. Okay, so to conclude this seminar, we are going to see a little section of examples, which is not, in fact, a section of examples in which we are going to see specific examples. What we want to do in this section is a method to construct examples of weak-twisted relative Rota-Baxter operators whose associated cocycle is non-trivial. That is, whose associated cocycle is not the identity. So the main result is this one. If we have D a Hopf algebra and Q from D to D a coalgebra morphism, then if this equality here holds, Q tensor Q with mu D is equal to Q tensor identity of D with mu D with Q, then this triple identity of D from D to D sub Q, where this D sub Q is this non-unital by algebra over D, where the product is defined in this way, mu dq equal to Q tensor D with mu D. The action is the trivial action of dq over D, and then Q is going to be the cocycle itself. Then this triple, under these conditions, is a weak-twisted relative Rota-Baxter operator. So thanks to this example, the problem of finding examples of weak-twisted relative Rota-Baxter operator whose cocycle is non-trivial is reduced to finding a coalgebra morphism Q from D to D such that this Q is not the identity and also satisfies this condition 3. So what we notice is that always that we have an idempotent Hopf algebra morphism Q from D to D, which is idempotent, then this condition 3 is satisfied by Q. So the problem of finding weak-twisted relative Rota-Baxter operators whose cocycle is non-trivial is reduced to find an idempotent Hopf algebra morphism different from the identity. Okay, so in this, to conclude, we are going to see a method to construct such idempotent Hopf algebra morphism, which is going to be given via factorizations. So we are going to see first the proof. If we have D any Hopf algebra, then we are going to see that factorizes as a semi-direct product of two Hopf algebras, A and H. That is, if there exists an isomorphism of Hopf algebras, omega D, from the semi-direct product of A with H to D, then in this setting, we can always associate an idempotent Hopf algebra morphism defined in this way. So what the theorem says is that any factorizable Hopf algebra D induces an example of weak-twisted relative Rota-Baxter operator by using the previous result. And with this, I finish. Thank you very much for your attention, and thank you for attending the seminar today.
Thank you for your talk. Other questions? There's a question in the chat.
Yeah, I am seeing the question of
Yeah.
Paolo. What can be said in the non-commutative case? Yes, it's a very good question. And I mean, I think that you refer to the functors, and what I can say is that if you don't assume co-commutativity, then the functors are not going to be well defined. So this functors does not work. So the co-commutativity is an essential hypothesis in these results. Maybe something to explore is if these two functors work imposing some condition of quasi-triangular of these kind of things, but I don't know. I don't know what happened in that case. What I can say is the commutativity is an important hypothesis in the results.
Thank you. More questions?
Can
One
Rota-Baxter
more question.
operators be directly defined on the Hopf brace? I mean, I don't know if you can reformulate the question, because Rota-Baxter operators are morphisms between Hopf algebras. So I don't know what do you refer on the Hopf brace, because Rota-Baxter operators gives like another description of Hopf braces. Under some conditions, the categories are equivalent. So I don't know what you mean.
So let's wait, maybe.
Yeah. Maybe he is writing.
Yes, maybe he will be formulating.
Thank you.
Mhm. Okay. Other questions, remarks? Well, okay. Thanks a lot again for your talk, and to all the
Thank you very much.
participants for attending this seminar. And I wish you a good, productive week. See you next Monday. Bye-bye.
Thank you. Bye bye.